I'm going to restart my multivariable calculus series that I was trying to make. I don't think anyone really noticed, but I'm going to restart it using Stewart's, calculus, right? So you don't need to read the book to follow along. I'm just going to use chapter 12.1 to as like a reference point of like what we're studying, right? So I'm getting the content from the book, and I'm also using the note sheets provided by my school's Calc 3 department. So not my notes or anything, not my knowledge. I'm getting this from a textbook. But to kick things off, we need to understand the 3D coordinate system. So the beauty of Calculus 3 or multivariable calculus is that now we're not just looking at 2D spaces, we're looking at 2D planes, right? We're looking at 3D space. And hey, I don't know if you know this, we live, breathe, and exist within space. So it's important to understand how it works. I'm sorry for the stutter there, right? In the 2D plane, we could define a point, right, on the 2D plane. We could say, hey, this point P, right, is defined as if you go a distance, A, and then if you go up a distance B, boom, you have a point P, and the coordinates are going to be A and B, right? So A represents your X, right? And then B represents your Y. So this is really your, X, Y form. In 3D space, you're doing the same thing, but now you're working with a new dimension. It's called three-dimensional, it's called a three-dimensional coordinate system because there's that third kind of parameter you need to define a point. Only two parameters here, your X and your Y. Now we have the Z. First of all, this is how the coordinate system is defined to look. You have X going, I guess you could draw at different angles, but the idea is that if you have X and you have Y, you have to curl your fingers from X to Y, and that gives you the direction of Z. That's called the right-hand rule, and we're gonna definitely use it more in this course, but that's just for you if you see, if you want to draw it yourself. You have to draw X and then Y and then Z. So for this, you're doing the same thing, right? We're going a distance A initially, right? And then we're going a distance B, but now we can choose to also go some distance C in that Z direction. C and Z, wow, they rhyme. So point P, right, it's going to have coordinates X, Y, Z, which in this case will be A, B, C. So that's, the gist of basically the foundation of this entire class, right? Working with the 3D coordinate system. The thing is that with the 3D coordinate system, you can have projections, right? Imagine, the YX plane, right, is really just us looking down the Z-axis, right? If you imagine looking top down from the Z-axis, you're looking at just Y and Z, like a bird's eye view. So the projection, so I guess I should write this down. The projection, this is sometimes what we'll do is we'll say, well, the projection on the XY plane of point P is just, it's going to be A and then B, but remember, you're looking top down. So you can't really, if you imagine looking top down, you're just getting this YX plane, but with now the Z-axis pointing out of the page, right? So you can't really see whether it's the Z-axis, you can't tell if the C value is towards or through. You can't really determine the value of C looking top down. So the projection is just really considering A and B. So you get A, B, and then 0. 0 just indicating, this is a projection. We don't know what the C value is using the projection. If we were to project point C onto the XY plane, you get a point right here, right? This is just A, B, 0, right? So if we were to project it down onto that plane. So this is the XY projection. You can do the same thing, right? If you imagine looking at the ZY plane, right? At the YZ plane, well now, X points out of the page, so you can't really think about A, but you can see B and C, right? So for YZ, it would be B0 BC, and that makes sense, right? Because if you were to project it onto that plane, the x value is 0. And then for, you can probably figure out the pattern out. For x, z, it would be A0 C, because when you're looking at if you're looking this way on the zx plane, you can't really, you can't really see B. You can only see A and then C. So the B becomes 0, and if you were to project it, like boom, like if this were the plane, right, it would have a value of 0 in the y direction. So those are projections. Just wanted to quickly go over those. Next, we're gonna start introducing surfaces. So just a real quick thing. Hopefully you kind of understand how you can approximate. If I give you tick marks, right? So if this is one tick mark and this is one tick mark here, you can kind of figure out that, hey, you can kind of, it's kind of hard to do it like for sure, right? Because of perspective and stuff, right? But you can kind of be like, okay, well, this is probably, this actual ABC, this is probably 2, right? Because you're going 2 this way, 3 this way, 4 up. Once again, can't really for sure because it's just perspective's kind of hard. But yeah, that's just, keep in mind, that's just kind of how it works. So in 2D, a curve, a point, an equation, the graph of like an equation, right, with x's and y's, we call that a curve in 2D. But now when you have the z, now you're dealing with surfaces. That's what we call them. A graph containing points x, y, and z, and with an equation, like if you were to graph an equation with x, y's, and z's, you get a surface. So a common surface you'll see is a plane. So the most simple plane, and we'll study planes more, but the most simple plane is something like z equals 3. And what this is saying is that for all points in space, we're just graphing the points that really have a z value of 3. So if you think about it, well, hey, something right here would have a z value of 3. Something here would have a z value of 3. Something here would have a z value of 3. And you just get a bunch of points that all have a z value of 3. What do you eventually get? Well, you just get a plane, right? A plane contains all points that would have the z value 3, right? Independent of x and y, right? This equation doesn't have x and y. So whether your x, y coordinates are here, whether you're here, whether you're here, all of these points still have a z value of 3, right? So it's a plane that just covers everything. Same thing for something like y equals 5, right? So for y equals 5, remember this is x, y, z, right? It's just all points that have a y value of 5. So it's independent of the other variables, right? So if this was 1, 2, 3, 4, 5, right? This plane is all the points that have a y value of 5. Even if your z value is -3, if your x value is 5, it doesn't matter. This is all the points that have a y value of 5. So it's another plane that now kind of stretches, kind of like, it's like parallel to the xz plane, right? So keep that in mind. We're going to talk a little bit about lines now, and we're just previewing these things, right? We're going to study lines and planes and other surfaces more. This is just a preview how we can use the 3D coordinate system to kind of like draw these 3D representations. Let's say do a line, right? Will kind of look, something like this. But, if you have a line, like if this is a line L1, right? It's actually pretty hard to tell, like, which way is it going, right? Because is it like going towards the page? Is it going out of the page? Is it you can't really tell its direction, right? Because with that third, dimension, maybe it's like, directed all sorts of ways. So what we use is called a projection. So a projection or why am I explaining a projection? We were working with projections just earlier. You can project this line onto a certain plane, and you can do it on the XY plane, right? That's, it'll kind of work the easiest if you do it like that, because you'll see in a second. So this is a projection of this plane, right? So, or of this line. So really, it's gonna be kind of hard to visualize this, but every point, if you were to project every point onto the XY plane, you get this L2, which is like the projection of the whole line. So if you think about all right, wait, how do I do this? Okay, this is gonna be kind of hard to visualize, but in the XY plane, this is showing that my line is actually gonna look, so if this was my axis, right, my pen representing the line, it's gonna be angled this way on the YX plane, right? Because it's like kind of angled this way, right? If you can kind of tell. And then it's gonna be angled this way. So my line is really like going in, like it's directed like into the page almost, basically, right? So hard to visualize, but that's what makes this class so challenging anyways, is just like visualizing these 3D things. But you will get better at it, I promise. But you can actually use this projection to figure out, like, hey, when does this line cross the YZ plane or the XZ plane or the XY plane, right? Because each point, right, if you, like, for example, let's say you wanted to figure out, well, what is the coordinate of this point, right? Let me get some coordinates going. Not to scale, I'm sorry, but we'll live. How do I figure out what's the coordinate of like a point right here, right? How do I figure that out? Well, you can use a projection, because a projection, right, the point just goes directly down to this line. So, right, because it has the same x and y, but now the z becomes 0, right? That's the projection of the xy plane. So, you could figure out, oh, this is around 3 here, and this is about 1 here, and then the projection, right, it's 0. So the actual coordinate will be 3, 1, and then whatever we can estimate about the z value, which looks to be about maybe, shoot, I don't know, because like it's like this distance, right? So I guess maybe 5, I don't know, but we can use this projection to figure out, well, when does it cross the YZ plane, right? Because when it crosses the YZ plane, that's when the y value is going to be 0, right? This is the YZ plane right here. So when the y value is 0, that's when it really crosses the YZ plane. So right here is when the y value is 0 on the projection. So the actual point where it crosses the YZ axis will be right here. And then same thing, when does it cross the XZ plane? That's when the x value is 0, right? It's going from x positive to x negative, so that's when it's crossing that plane, essentially. So then, wait. I'm so sorry. It's when the x value is 0. Right, it's when you cross the YZ when the x value is 0, you cross the XZ when the y value is 0. And you can see that, right? Like when your x is really 0, right? When your x is 0, or when your y is 0. My fault. I could tell something felt off about that. I'm sorry. But you can see right here, this is when it's crossing that, the y or the x-axis. So right here is when it's crossing the point. So projections are helpful, right? That's actually why we use them. So let's quickly just go over some other surfaces too. So for example, if you had the surface, let me use black. Let's say you have the surface x squared plus y squared equals 9. Well, we know that in a plane, this will be a circle, right? Because this is really a statement of Pythagorean theorem. For every x, for every point on this curve in the 2D world, the distances from the origin will end up equaling, if you were to sum those, if you were to sum the squares, it would equal 9. So every point is basically a distance 3 from the center, but that's just a circle. So, the same really goes here, but now the difference is, you have a circle right here where when z is equal to 0, but, right, because this is when the z is equal to 0, this is on the xy plane, but now z is independent of this equation. So for no matter what value of z we have, we still essentially get a circle on that z value, right? So if I could draw the same circle for every value of c, well, what does it kind of look like it's forming? This is really forming a cylinder, right? For every point on this cylinder, we have the same deal where the sum of the x or the square of the x plus the square of the y equals 9. So every point from the z-axis is equidistant by a value of 3, right? But now we're extending this upwards, right? You're taking a circle and you're extending it upwards because the z value doesn't matter. You still get the same circle for that z value. You get a cylinder. If you think about, well, what about z equals y squared? Same deal ish. This looks like it would be a parabola, right? And if you think about the y, the x, and the z, you would get, for the yz plane, you would get a parabola. But now, if you have an x3, right? For an x3, well, hey, it's independent from the equation. So it doesn't matter if x equals 3, I still get the same z equals y squared, which would look like a parabola. So essentially, what I get is something, this is kind of hard to draw. Yeah, something like this, which is kind of like a parabola extended across the x-axis, right? So this is actually what we call a parabolic cylinder. This is actually a cylinder, believe it or not. A cylinder, we'll talk more about this later. A cylinder is just any surface that contains lines that are parallel to some sort of axis or some other sort of line. So in this case, all of these lines are parallel to the x-axis. All of these lines are parallel to the y, or to the z-axis. So those are just what makes them cylinders. This is just a regular good old cylinder. This is what we call a parabolic cylinder. Now, we're talking a little bit about this idea of points being equidistant from one another, right? And that's forming a circle in the 2D world. But if you do the same thing in the 3D world, right? If you think about points that are all equidistant in 3D space from the origin, right? If you think about this x1, y1, z1, and if you think about a point right here, x2, y2, z2, if they were all equidistant from the origin, if these 2 points were equidistant from the origin, then you would get a sphere, right? So really, if you think about Pythagorean theorem in 3D, it kind of looks like, okay, so if you have an A here, a B here, and a C here, what's the distance? What's this distance from the origin to the point? Well, really, this is going to be kind of hard to visualize. This is just kind of a right triangle right here, right? So if I were to draw this right triangle, you have a right triangle with one side that's C and then this other side. Well, this other side is going to be the hypotenuse of this right triangle with A and B. So that the hypotenuse of that is square root a squared plus b squared by Pythagorean theorem. So you can do the same thing, right? Square this side, a squared plus b squared plus c squared, right? I took the square of this, right? And that gives me this distance d. So yeah, squaring that cancels out the square root. This is really the distance formula. Or if I were to take the square root on both sides, I get a squared plus b squared plus c squared. Now, if I were to shift where I'm taking the distance from, if I were to take it from another point right here, then I would have to think about like the distance, like a minus, like, let's say this is like a1, or let's say this is like x1, y1, c1, right? I would really have to do then square root, I'll just do x, right? X minus x1 squared, right? Whatever this x value is, minus the x value here to get that x, that total x distance. Same thing for like y minus y1 squared, or z minus z1 squared. So this is a distance formula. This is an application of Pythagorean theorem. And then using this, you can actually get an equation of a sphere, right? And the equation of a sphere for centered about the origin is x squared plus y squared plus z squared equals r squared, right? These are all points that are a distance r from the origin, right? And that's a sphere. By definition, all points on a sphere are equidistant by a radius r from the center. And then if you obviously offshift your center, you would get x minus 1 squared, or like x minus h plus y minus k, and then I think for z it's L, I think that's the letter, L minus z minus L. So same thing, but now your radius is, or your center is HKL, right? Everything's been shifted by that much. So yeah, for one last kind of, I guess, problem, I can walk through it actually, it's not too bad. Let's say you had an equation like, this is from the book, x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0. This is actually the equation of a sphere. And how can you kind of get it into this form right here? You have to complete the square, right? Because we have right here an x squared plus a 4x. And then we just need to add on, I'm going to use different markers. We just need to add on, let me see if I can do the black pen, red pen thing. I don't know if you guys, or whatever his name is, you can do like that thing where you can switch markers, right? I now have x squared plus 4x, so x squared plus 4x, and then to complete the square, to get this x minus h squared form, I would divide it by 2 and then add the square of that, right? So I would add plus 4, because I'm really doing, divided by 2 is 2, 2 squared is 4. And then I have my, my y squared minus 6y, and then divide that by 2, that's 3, or negative 3, square that, that's 9, so plus 9. And then I have the plus z squared plus 2z, and then divide that by 2, that's 1, square that, that's 1, so now I get the plus 1. And then I still have that plus 6, but everything I added in blue is stuff that I added to the left-hand side. So I got to add it to the right-hand side so that both sides are still equal, right? This is still an equation. Both sides need to be equal. So I get 4 plus 9 plus 1. Now I can start sort of doing my x plus 2 squared, right? I know I can kind of change this to x plus 2. And when I square the binomial, I will end up getting x squared plus 4x plus 4. And then I do the same thing, right? Y minus 3 squared, right? Divided by 2. That's that negative 3 part. And then plus z plus 1 squared, right? I always divide it by 1, and that gives me kind of like that thingamabob, that like the I don't know what you call it, but it's like that z plus 1 part, that 1 comes from dividing the middle term by 2. Because when you square it, you would end up having to like add it to itself again, and that's where that 2z comes from. So yeah, that's just completing the square. And now this stuff, this is just 13 minus, or 14, right? 4 plus 9 plus 1 is 14, minus 6, because I'm going to subtract that 6 over, I get 8. So this is really, with just using some algebraic manipulation, this is really a sphere with center -2, 3, -1, and a radius of root 8. So yeah, that, and then you can use the distance formula to figure out, like, let's say there's a point, like, is 0.472 on the sphere, right? Well, to figure that out, you can use distance formula from the center. I know that square root, right, if I do square root 4 minus -2 squared, right, I'm using the distance, I erased it. The distance formula is x1 minus x2, right, squared, right? So x1 is 4, and then x2 is -2, so 4 minus -2 squared, and then 7 minus 3 squared, and then 2 minus -1 squared, right? So this will equal some distance. I get 6 squared plus 10 squared plus plus 3 squared is going to end up equaling it should end up equaling root 8 if it's really on the sphere, because it would be then like a distance root 8 from the center. But yeah, this won't end up being true, right? We can tell this is going to definitely be much larger than the actual thing, or the actual like radius. And well, hey, what did you notice? Well, this is the same as doing 4 minus -2. That's the same as doing 4 plus 2, 7 minus 3, z plus 1. That's the same thing as just plugging in the number into the sphere equation and then seeing how does that total value compare to 8. Is it going to be greater? Is it going to be less than? So I can tell this is going to be outside the sphere, right? Because this is a distance greater than root 8. So yeah, that's the 3D coordinate system. Hopefully that made sort of sense. I don't know. Hopefully it wasn't that bad.